So we're going to take a look at section 1.5, which is all about something called the existence and uniqueness theorem. And as you might imagine, it has to do with two things. It's proving that something, a solution to a differential equation, exists, and that it is a unique solution. And in mathematics, proving that something exists is kind of important, but proving that something is unique gives you special superpowers. So for us, we're going to start off with a little example down here, but in order to kind of put this into context, if solutions to a differential equation don't exist, then there's really no point in trying to approximate them or try to find an analytic solution for them. And so knowing that a solution exists is important. And if a differential equation is supposed to model a physical system, and that solutions don't exist to that differential equation, then that means you should have serious doubts about the model. If you're trying to model a real-life situation and you can't find solutions that exist, then you're in a bit of a pickle. So we're going to take a look at this example right here, which says, without graphing, try to figure out what the solutions are to this polynomial equation. Right? So we've got 2x to the fifth minus 10x plus 5 equals 0. Now you may know some algebraic trickery to be able to solve this, but most of us look at this and say, ugh, it's more than a cubic. Ugh, no. Most of us kind of just don't even think that that's even worthwhile. But it turns out that you should remember there's this thing called the fundamental theorem of algebra. And the fundamental theorem of algebra says something really important. This must have 5 solutions because it's to the 5th power. Now, some of those solutions might be repeats, and some of them might be unreal, meaning complex, but it definitely has 5 solutions. But the fundamental theorem of algebra steps in and says, don't worry, solutions exist. Right? Guaranteed 5 solutions exist. That's the highest degree of the polynomial. So one of the ways that we kind of set our mind at ease is using this theorem and saying, okay, I know there's 5 solutions. It's just a question of whether any of them are real or whether any of them are repeat solutions. So one way we might approach this problem is to kind of get into the weeds and say, well, what if we substituted values of x? What if we substituted a value of x equals 1? In that case, it would be 2 times 1 to the 5th minus 10 times 1 plus 5. And notice I'm not substituting it in and saying it's equal to 0 because I don't think that that's going to be, I don't think I would just guess the right answer. But notice what this gives us. This becomes 2 minus 10 plus 5, which is negative 3. And this one here, if you sub in a negative 1, 2 times negative 1 to the 5th minus 10 times negative 1 plus 5, this gives us positive 13. Now you might think, okay, big deal, we just plugged in 2 numbers. But notice, if I plug in an x value of 1, I get a negative number. And if I plug in an x value of negative 1, I get a positive number. That means the graph of y equals 2x to the 5th minus 10x plus 5, that if I were to graph that, it has to go from negative at x equals negative 1 to being positive at x equals negative 1. So that means we can expect there's got to be a 0 somewhere between there. So if you imagine x equals negative 1 and x equals positive 1. When x equals negative 1, we expect a positive 13, right? Way up here. And when x equals negative 1, we expect a negative 3. Which means that whatever the function does, whatever that graph does, it must cross somewhere in between x equals -1 and x equals 1. It doesn't have a choice because, of course, this thing is a polynomial, and polynomials are continuous. So since it's continuous, and since we know it has to have solutions, 5 of them exactly, and we know that it's negative in one location and positive in another, then it must have a solution somewhere between there. So there must be a solution between x equals -1 and +1. Doesn't have a choice. There must be a solution. So this is handy because we're able to use that fundamental theorem of algebra and say we're guaranteed to have solutions. They exist. And then we know some other things about the fact that it's a polynomial, and we can put it together. We can create an argument and say there must exist a solution between here and here. I don't know what it is, but I know it's some value of x between -1 and +1. So what we need at the bottom of this page here is some kind of a similar situation, but for differential equations. And that's where the existence and uniqueness theorem comes into play. So we're going to take a look at the next page and see how that works. So on page 38, we introduce the actual existence and uniqueness theorem, and we go about it in some important ways. So the first thing that we're going to do is take a look at what's required. So given, these are the two givens, given that we have some differential equation, and notice this differential equation could be in terms of both variables, or it might just be in terms of one or the other. But the possibility is you've got a differential equation in terms of an independent and a dependent variable, and you also have some stated initial condition. Right? So given an initial condition and a differential equation, and then here comes the big theorem statement. The theorems in mathematics almost always start with an if. So if that differential equation, and I don't know why it keeps coming up wrong on here. This should be the partial derivative. Apologies. That's the partial derivative of f with respect to y. If both of those are continuous functions in a rectangle, and the rectangle is defined over t and y as being between two t values horizontally and between two y values vertically, right? So if you have a rectangle in the ty plane that contains your initial condition, right? So rectangle in the ty plane contains the initial condition. So if you have a rectangle in the ty plane that contains the initial condition, and these two things are true, this and this are both continuous. So similar to our polynomial example on the previous page, we have to know that there's no jumps, there's no gaps, there's no places that we have to worry about. So as long as the derivative, the differential equation, and the partial derivative of that differential equation with respect to y are both continuous, then you have this rectangle. And so what that might look like, let me draw a little picture here to see what it might look like. You've got your y direction, your t direction. This is your yt plane. And so what we're going to do is we're going to create that rectangle that looks like this. So between some t value a and some t value b, and then some y value c and some y value d, you have this lovely little rectangle. And you'll notice I'm just creating a little dotted line for the rectangle. And somewhere inside there you have your initial condition, right? The point somewhere inside there is t0, comma, y0, right? And notice that it says it has to be inside, it has to contain the point. So that means it's got to be inside the rectangle. I'll just write inside in here. So if all of this is true, then, and then we have a then, and mathematical theorems always start with an if and then conclude with a then. So if all of this is true, then the initial value problem has a unique solution. So this is our guarantee, has a unique solution in some interval around t, right? Where t is right around our initial condition. This symbol right here is called epsilon, and so epsilon is greater than 0. So this is just saying right in the vicinity of the initial condition. Right? So notice it doesn't guarantee that the solution is unique everywhere and that it exists everywhere. It just says right in the vicinity of your initial condition, you're guaranteed. So basically one way of saying it is in the rectangle, you're guaranteed to have an initial condition, or excuse me, you're guaranteed to have a particular solution that goes through that initial condition. Right? And so this guy over here, this epsilon, is just basically the error factor in the independent variable. And it's tiny. It's designed to be a small little gap. So right in the area of your initial condition, you're guaranteed to have a unique solution. Now for our purposes, this is really more of a weapon than we need for everyday purposes here. But really, this is just guaranteeing us that as long as we can show that our differential equation and the partial derivative of our differential equation with respect to y are continuous, and we've got an initial condition within some kind of rectangle, within some view, then there's going to be a unique solution in that view. So let's see how this plays out and what this really means on the next page.